We are the Columbus section, joint chapter of the Solid State Circuit Society and the Circuits and Systems Society. We've been around for about a little more than 4 years, about 4.5 years now, putting on these workshops, having technical talks, things of that nature. We have the final workshop of this year tonight, and the final workshop of our Tiny Tapeout series happening right now, and we're prepping for a tapeout on November the 10th that some of you have signed up for and are receiving sponsorship for, so thank you for doing so. We'll try to get as many people sponsored as we can. This is the opportunities for engagement that we've had throughout the year. On the left-hand side, this is the Arduino starter kit option that we've been sponsoring. So starter kits up to $100 for a solid state circuits contest. That ended in August of this year, but they run it every year, and we plan on continuing sponsorship of this on a yearly basis. So at the end of this presentation, we'll send a QR code and a flyer out and an email for all of you that have attended. So that if you want to sign up for sponsorship and apply for sponsorship on that front, that you can. Also, the one that you're here for, Tiny Tapeout, we're sponsoring, we can sponsor, you know, lots of students, and we have ideas for extending this workshop into, you know, more of a single workshop format for next year. We had a workshop earlier in the year that covered an intro and some of the basics of submitting through Tiny Tapeout, but we're going to condense all this down into single workshops where by the end of the workshop you have a submittable design, and if you've made it through the entire workshop, then you'll receive sponsorship from us after filling out a form. So that's where we're going. So that kind of leads into this slide. The next workshop will be in April of 2025, where we'll be prepping for an early June Tiny Tapeout run. That date's not finalized yet on Tiny Tapeout's side, but it should be sometime in early June. We're doing something a little bit different for this, in that a small entry fee will be required to enter the workshop of $5. This is just to get some more active participation, and this $5 will secure you a sponsorship spot should you complete all of the conditions for sponsorship that are outlined here. So sharing your GitHub repo link to make sure that you pass your design passes all the Tiny Tapeout checks that's on the link, GDS test and documentation. And we'll sponsor a 1x1 tile and the PCB. Any additional tiles or analog pins will be the responsibility of the participant. So that's running next year. We'll have a link on the next slide and a flyer, and this flyer will get sent out in an email at the end of this workshop as well to everybody online and in person. Here is that flyer. It's a good looking flyer. This link actually, this sponsorship form actually for the Arduino kit and the Solid State Circuit Society contest that I mentioned, both of these can be applied for through this QR code here on the bottom right, as well as the Tiny Tapeout. This flyer, as I said, will get sent over email and after this workshop, and will be in these slides, so you'll have several opportunities to grab it and apply for sponsorship if you want to.
Gus, you mentioned, yeah, just back to the flyer again. So if you actually go to that link, you will see these conditions reinstated in the Google form. But very important point, if you actually come to the workshop that we're going to have in April, you and have your tapeout and database ready for tapeout according to the conditions that we have there, we will sponsor you. So you will get sponsorship if you are tapeout ready in April 2025. You will get a sponsorship on that day. All right.
That is the most important point. Thank you for reading that, Rami. Okay. On the topic of sponsorship, we are also looking for sponsors as a chapter. We've had a generous sponsorship from the CAS for the last 2 years to have all these workshops and distinguished lecturers come in and give talks. They continue to fund us, but we would like to, broaden our sponsorship portfolio. Also, we receive a lot of generous funding from the Solid State Circuit Society. We won an award this past year that's, reinvigorated the funding from them, and we get a yearly subsidy as well. And then Sensix Corporation here at the bottom has been a sponsor of many of these workshops as well. If you're interested in sponsoring, we have, several ways to reach out on our website, and then more directly is just at this Gmail account right here, and we'll definitely field your requests. If you want to be actively involved in planning workshops or having lecturers come in with your sponsorship, or if you just want to be a kind of a silent sponsor, anything, we'll consider, you know, kind of any involvement, any creative involvement that you come up with. And then thanks to everybody for a great year. This has been the best year so far for the chapter. We've had a lot of talks, a lot of events, a couple workshops. We've won a Best Educational Program Award from the Solid State Circuit Society, and it's just been a fun year for us. So thanks everybody for making that a reality. And without further ado, I'll turn it over to the guy in the bottom left of the screen right here, Sam Ellicott, to go through the Tiny Tapeout Workshop 2 and the tutorial.
Okay, thanks, Gus. Yeah, that picture's really old, by the way. Just FYI. Okay, so as Gus mentioned, today is the second of our series of workshops on Tiny Tapeout. So just as introduction, the goal for today is we're going to hopefully go through a bit of the Tiny Tapeout flow and end up with a design at the end. So a little bit about me. I'm the Columbus chapter webmaster. So if you looked at the website, that's mostly me, although a couple of other people have done some work on it. Or if you email the chapter, that usually goes through me first. So, okay, I'm a PhD student at The Ohio State University. I work at the CLAS laboratory, so the Circuits Laboratory for Advanced Sensors and Systems. I'm focused on RF and mixed signal integrated circuit design, and my PhD thesis is on true random number generators and a little cute block diagram of the one I'm working on there. I graduated with an electrical engineering degree from Cedarville University in 2019, and I've interned at Analog Devices a couple of times. So just by way of reminder, the overall series goals is to understand the workflow for using the open source tools to do digital flows specifically. I want this to be a nice hands-on introduction to digital design, so today is going to be a crash course in Verilog and writing and testing simple Verilog modules, and we're going to make a simple project, and finally, we want to have fun with this. So last semester, this past May, we did our introductory workshop, and then today is going to be the tooling in the series project. And due to just logistical reasons, things got pushed back. We aren't going to do this third workshop. So what happened in the first workshop was we had a brief history of integrated circuit design. We had an introduction to digital design, what the digital flow is actually doing. And then finally, an introduction to what Tiny Tapeout is and sort of a little bit of how to start using it. Today, we're going to be talking about more about tooling and the series project. I'm going to start with a review of Workshop 1 because it's been like 6 months at this point. And then we're going to set up a Tiny Tapeout project, write some simple Verilog modules, and then write some simple Verilog test benches. And the goal is to have a little digital desktop clock by the end of this today. So what are we trying to do at the end of the day? What we want is, with digital design, we want to take a concept, some behavior, algorithm or behavior, et cetera, and then convert that into a digital design. So that looks like, say, we have like an encryption algorithm. We have that in code or as like a block diagram. And we want to run it through some program or tool, and then we want to get out a design that we can have manufactured at the very end. So what we're doing here is we're running it through the digital design flow, in this case, OpenLane. So in a little bit more detail, we'll start with code. In Verilog code, we're going to run it through a tool, and that'll generate an elaborated design. And that's going to be just generic gates, flip-flops, AND gates, OR gates, et cetera. And then we run that design through another tool, and that adds in what are called standard cells. And these are the actual bits of logic that are in the manufacturer's guidelines that actually get manufactured. And then we stitch those together into a final design. And we have software that does all of this for us. So in even more detail, what we have is we have our Verilog files, we run it through OpenLane. And then OpenLane does that process for us, and it spits out what's called a GDS file, which is the files that we send to the manufacturer, in this case, Skywater. We're going to be dealing with this part, which is going to be writing Verilog files and then doing the elaboration and functional simulation. And Tiny Tapeout via OpenLane handles most of the rest for us, and it runs the timing analysis and then spits out GDS. So Tiny Tapeout what is that in particular? Because that's all previously was just digital design in general. Well, Tiny Tapeout is a cloud-based design suite. It runs OpenLane through GitHub, a series of GitHub actions so that it reduces the amount of tools required to start. And how it works and how it keeps the costs low is it's able to, it shares area, because this would usually be just one project design, and you have just your little project that's floating in the middle here, and you have to pay for all of this area, even though you're only using a tiny little bit. So what Tiny Tapeout does is this series of interconnects that allows that one piece of die area to be shared between about 500 different projects. And this allows people to tape out designs in a much less expensive fashion. And so when we put a design on Tiny Tapeout, what we're buying is one of these little slots here. So this is a 1x1 slot, this is a 2x2 slot, and these are all 2x1 slots. And so what we'll do is when we submit a design, we will get allocated one of these slots, and our design sort of fits in there and gets hooked up to this bus system and gets connected to a series of I/O pins. And then if we order a PCB, we get this system back, and that sets up power and all of that other niceties for us so that we can test our design easily. So Tiny Tapeout, this is what we get when we have a single tile. So we have about this much area, which is enough for about 1,000 gates. And like I said earlier, you can buy more than one tile. And then this is what the interface to Tiny Tapeout looks like if we're at our level. So this is what we get when you get a Tiny Tapeout slot. We get a clock pin, a reset pin, 8 inputs, 8 outputs, and 8 bidirectional pins, so we can select whether they're inputs and outputs. So that's that's basically the information that got covered last time. If there's any questions on that, I'm more than happy to answer them. But if everybody's more or less, I feel like that information can easily be found online, et cetera. So I'm hoping everybody's fairly familiar with all of those concepts. But yeah, so if there's no questions online, I think I will get started. Okay, so what we want to do tonight is an introductory project for Tiny Tapeout. So the idea is that we can design a 7-segment digital desk clock display that is just the bare bones for a desk clock. So 24-hour time format, you can set the time, and it outputs to 7-segment displays, and that's all you get. So I've broken this design into modules, and I've provided some of them for you, but also some we're going to complete together. And then I also have test benches for each of these modules. So here's an overall block diagram of the system. Hopefully people here in person can see this on the screen. But what we have is we have inputs. We have our clock signals that feed into the design. This is our global clock signal. And then we have a reference clock, which is used to run the clock at an accurate pace. The system clock doesn't have to be an accurate timekeeping. Then we need a method to set the time. So we have pins that allow us to set the hours and the minutes and select via a fast set or a slow set. Next, we have the a register that just holds the time. So we have the hold the time in a 24-hour format. And then this needs to overflow counters at the appropriate interval. So at 60, after 60 counts, the seconds overflows, the minutes overflow, and then every 24 cycles, the hours overflow. And also needs to handle time setting functionality. Oops. And then next, we actually have to display the result on a 7-segment display. We don't really have enough pins to directly control 6 7-segment displays. So we have to shift it out, and this gets handled by a module that takes data in as SPI data, and then we can use that to control a series of 7-segment displays. So in slightly more detail, we have a system clock, and this is running, all the modules in the system are running off of the system clock. And so this is the main timekeeping, or the system clock is the main source of synchronization between all the modules in the design. Second, we have a reference clock. This is running at a very specific frequency. So this happens to be running at 2 to the 15 hertz, which is, will be a handy number in a little bit when we get to actually trying to build this thing. And then this is, as stated previously, this is basically the, this is what's keeping the timing accuracy of this clock. So as long as this doesn't drift, we have an accurate clock. We have a couple other modules in here as well. So what happens if the reference clock and the system clock are slightly skewed from each other? In digital design, if that happens, bad things occur. So what we want to do is we want to synchronize those two clocks to each other. And what we have is a little module here that performs that operation. If you can see this little waveform view we have here, in this test bench, we have the reference clock, and it's just kind of has a rising edge just somewhere in the middle of our system clock. Then after this reference clock synchronization block, what we get is we have a rising edge that's slightly delayed from the incoming signal, but it's happening exactly at the same point as the system clock. And also, if you have any questions, just feel free to interrupt me. I think online you can unmute, and it should go out through the speaker system, or you can type in the chat. OK, so next, we need to generate signal events for updating the clock. So in this case, we have this module that takes our reference clock in and generates output pulses at appropriate times. So we have an output that generates a single width clock pulse once every second. And then we have two other outputs that generate pulses at relatively increasing time frequencies for allowing us to set the clock quickly and set it slowly. So that's at 2 hertz and 8 hertz respectively. If we zoom in on that signal even more, we see our clock strobe signal is exactly 1 system clock pulse wide. And that lets us control things nicely throughout the design. Then the real world is very messy. So we need to if we're taking a switch input onto our clock, we need to be able to handle if the switch is bouncy. So what we have here is we have this input debouncing circuit module. So it takes some random garbage on the input, and then it cleans it up nicely into one long continuous pulse for us. Next we have our, we need something to hold our time formats. This is, I feel like, pretty self-explanatory. And then finally, we need to output data to the display. And we're using this MAX 7219. And because this is an SPI module, we actually have to initialize this correctly. So we can't just shift out data to it directly. We need to, when we first start up the system, we need to set some configuration registers appropriately. And those are shown right there. And what we do is this module, whenever we reset our tiny tapeout clock, this will shift data out over to the display and set it up correctly. What are we going to do tonight? So what we're going to do is we're going to write this test module, write this module in Testbench. So this is the Strobe signal generator. And then I've also left it as an exercise to write this clock register module as well. I have the Testbench for this written already, and we'll see if we have time to get to it in the presentation. So, are there any questions about that? Or is that all clear? None online? OK. So what we're going to do is get started. So we're going to need to set up the tools in a project. We're going to write our strobe generation module in order to, and while doing that, we're going to have a crash course in Verilog and learn how to generate block diagrams. Then we're going to write the test bench for the strobe generator module, and we'll be able to view those results in Gtkwave. And if we have time, we'll repeat that for the clock register and then run tiny tapeout flow to generate us some hardware. So without further ado, we'll move on. So if you have a computer out and want to follow along, please go to this URL, and we want to use it as a template to make a new repository. So I am going to do that now. There we go. So we want to go here. So what I'm going to do is I'm going to use this template, and I'm going to make a new repository here. So I'm just going to call this Clock 2024 Workshop. And it has to be public for GitHub, for Tiny Tapeout flow to work. So we're just going to start there, and we're going to run that. OK, so now we have our very own repository. Has everybody been able to do that? Yeah, that's what we're leading up to. So if you know how to use GitHub, yeah, you're just going to clone it. But if you're using Linux, just clone it anywhere. If you're using Windows, make sure to clone it into a directory that has no, to the same directory that you've installed the open source tools. Just everything I have set up assumes that the open source tools and the project repo are going to be in the same root directory. So just keep that in mind if you're following along online. So yeah. So oops, I lost where I was there. So we're going to open this back up. And OK, we're going to go over to here. And so what I'm going to do is I'm using Gus's laptop here. So what I'm going to actually do is it doesn't have Git installed. So we're going to use the tools that we have on the USB drive that you should have, that we should hand it out to you at the beginning. And what we can do is we can open portable Git. We're going to open Git CMD. So we have Git here. So what we're going to do is I'm going to go cd up a directory, so I'm in the root of the flash drive. And I'm going to git clone. We're going to go to code. I'm going to clone via HTTPS. And I'm going to copy that to the clipboard. I'm going to Alt-Tab over and paste. And this is going to clone this project. Is everybody following along OK in person? Where are you stuck at? Good? Well, we can wait for you to catch up. OK. OK. So we have that. We have it cloned now. So we're going to now, I'm going to open VS Code. So what I'm going to do is open folder. And we're going to open VS Code into that directory. And this is going to make our life a little bit better. Okay. Yes, I trust the authors because the author is me. Okay. So, yep, we have Git. There we go. So this should be set up now. So is everybody here? Does everybody have their source code open and able to access the source code? Okay. Never mind? Okay. Very good. So I'm going to go back to my presentation. Okay. So now what we want to do is we have our system down, we have all our code downloaded. Now we need to start up some terminals so that we can actually use the open source tools. So if we open up the directory, so this is the code that we're using, I can run this startup script. And so what this is going to do is it's going to open a terminal for me, and you see that we have this marker here that tells me that we have the open source tools running locally right now. And so I'm actually going to open up a second monitor here so that we can basically run two programs at the same time easier. I'll just copy that over. It's not, yes, good. Okay. So we have that going. Here we go. So if we go back over to GitHub now. So if you scroll down, note that we aren't running Tiny Tapeout yet. So there's a few things we need to manage on this to make sure that Tiny Tapeout actually runs as we expect. So we're going to go over to the settings page. So people in person following along okay? Good? Okay. So we need to go here, and we need to enable GitHub Actions. Now allow actions, so this is fine. And we also need to enable GitHub pages that are able to be deployed from GitHub Actions. So with that set up, we can go back to the code. Yep, and as you can see, we are now failing all of our tests. This is expected, and we want to fix that by the time we're done tonight. So to get started, I'm going to, so we've now set up GitHub pages. If everybody's followed along with that, fine, well. So what we're going to need to do is we're going to want to modify our info.yaml file, which is the configuration for Tiny Tapeout. So if we go back over to VS Code, we have here the info.yaml file, and you should change your author to be your name, and then we're going to want to change what the top module for the project is. So for me, I'm just going to put this as the name of the workshop, so it's going to be Clock 2024 Workshop. And then we're also going to change a module in the source code. So if we go to source, and this TTUM digital clock example. So we have to, over in here, I forgot that this doesn't have the Verilog extension installed. This is going to be a little bit sad, but this is going to be Clock 2024 Workshop. I'm going to actually install Verilog. This one is, I think, the one I have installed on my computer. Or is it? No, it's this one. Okay. So with that installed, hopefully, yes, that's much better. So, okay, so we have that saved. So basically what we've done here is this module name and this name in the info.yaml file need to match. And that's the first thing we have to do to just make sure everything works correctly. Next, so like I said, so we have to update some of our test files because we changed the name of a module. Now we need to make sure that Tiny Tapeout knows where everything is and what everything's named so that it can run correctly. So we need to edit this test, and it's going to be Tiny Tapeout tb.v. And so when we're running over here, this is a Verilog module, and we'll get more into what this is all doing later on in the workshop, but this is that same name again, and so this should be Clock 2024 Workshop. And that should just all be the same name there, and is there, yes. The last thing is, I changed that one already. Now, as I mentioned earlier, I've provided some template modules that we're going to be updating throughout the workshop. So we want to copy them over because they're not named what they should be. So if we go over to this input, so we have this clock gen template. This should be, we want to rename this to be just, to rename this should just be clockgen.v. There. And I think we'll end our configuration there for now. Oh, okay. I think we'll see when we actually push, but I think since we copied the template, GitHub Actions, I believe, are set up. So if I go over to here, so if we go to so we're just in the root folder for the repo. If we go over to settings, if you go to actions, so if we go to general, allow actions and reusable workflows. So this should be currently set up. I don't think you had to actually mess with anything there. The main thing that needed to be changed is we have to be able to build the GitHub pages and deploy them from a GitHub action. Good? Okay. So we've moved all these files around. And if the file hasn't gotten moved, it'll actually be obvious at a later step. So we'll hit it. And don't worry about taking pictures. I'll give you the slides at the end of the presentation. So, okay. So now we have our project all nicely downloaded. Now what we need to do is we need to start making changes. So this is the template that I've given you. So what we want to have, so in this template, we have a defined set of I/O pins. And this is what we want to be at the end, is we want to generate a bunch of strobe signals out of this. So how do we do this? So this is what we want our module to look like at the end. So this is what we want our block diagram to look like when we're all said and done. And it looks a little bit daunting at first. It's actually not so bad, though. So what we need to do is we break it down into smaller chunks. So we really want a counter and some strobe generators. So all we need to do, since we know that our input clock, our reference clock, is running at 2 to the 15 hertz, all we need to do is do a sequence of divide by 2s in order to get the correct clock frequencies. So if we divide our reference clock by 2 to the 15, that gets us a 1 hertz clock signal output. And then what we can do is we just generate a strobe signal on that rising clock edge, and we're good. We have a 1 hertz pulse. And all the other pulses that we need are actually sort of generated for free along the way. So we need to start with is, all we need to do is we need to learn how to write a counter. So this today is going to be a crash course in Verilog. Online, there are good resources for this. I have included links here for some of them. There will be slides posted at the end, just so you're aware, so you can access these easily. But for now and for today, you have me, and I'm sorry. So we're just going to cover the bare minimum for today's project, and I hope that this motivates you to actually go and dig into some of these external resources to learn more. So to get started is just some preliminary notes. What we're going to talk about is modules. So how do you write a Verilog module, which is sort of the base unit in Verilog? How to write sequential logic, so that's flip-flops, and some basic combinational logic. So just by way of note, Verilog kind of has C-like syntax if you squint. So statements end with a semicolon. We have case-sensitive names. So VHDL is case-insensitive. Verilog is case-sensitive. So if you name something stop with a capital S, that's different from naming it stop with a lowercase s. We have comments. They end with double forward slashes, and you have the slash star slash comments as well. And when we're writing blocks, so if statements, things like that, start with a begin and end with end. So instead of having curly braces, you have that. But it sort of looks like a programming language, and it kind of feels like C if you kind of are not being too picky. Just as a way of note, there is this syntax here, so you can have a begin block and then give that block a name, and that'll show up in simulators and stuff. I'm just giving that as a note so that if you see that in some of the source code, it doesn't freak you out, because that's I thought that was a little weird, but yeah. I'm not going to really rely on that, but just note that it's there. So what are we doing? We're going to open up this source input clockgen.v file. And then what we're going to want to have by the time we're done with this file is we want to divide our ref clock signal by 2 to the 15 and generate our 1 hertz clock pulse. And then we're going to generate also a 2 hertz pulse, an 8 hertz pulse, and a 4.096 kilohertz pulse. And we'll just tap out some values off of a down counter. And so what we're going to need to get started with this is we're going to need to write ourselves a 15-bit register that gets reset to 0 with the reset signal. And then we're going to count up by 1 on the rising edge of ref clock. We're going to come back to this rising edge of ref clock thing because we want to count because we don't really know how to do that yet. So for now, we're just going to count up on the rising edge of our input clock. So to be continued. Just a high level of this is just sort of for reference, Verilog modules. So we have a file. We want to start it with default net type none. This basically tells Verilog to give us an error if we don't tell it if our a variable is a wire or a register, and we'll get to that in a minute. And we have our input module. So we give our module a name. So this is module clockgen, and then we have our list of inputs and outputs. And by my convention, and this is common convention, inputs are prefixed with an I underscore and outputs by an O underscore. And then what we do is then we can define our inputs, what their type is, and down here inside. Note that we have module clockgen open parentheses, clothes parentheses, and then a semicolon. So this is one statement, and then all of the stuff is inside this module. So that's just by way of syntax reference. So in general, it looks something like this. So with that, okay, yeah. So I'm going to go back, and we are going to have a look at this. Yeah. Okay. So we're going to need this for writing our module. So when we write something that's using sequential logic, we're going to use what's called an always block. So this is going to be always pos edge, always at pos edge, and then the name of your system clock. And you want to always use the system clock. You may sometimes be tempted to not use the system clock here. Always use the system clock. And then what we have is that generates for you a flip-flop. And then what we can do is we can have various conditions on that we set our flip-flop high or low to. And then in these always blocks, you can have if statements and else if, and those are sort of act like normal programming language constructs. And then at the end, when we have a reset signal. So down here, and this is below everything else, we have our reset. So this is when we want to set the initial state of our flip-flop. This is a little different from if you're doing FPGA design. Usually you just set the state in here, but because we're doing ASIC design, we have to have more of a global reset situation. Okay. Also, a very important note is that if we're in this always block, and specifically this always at pos edge block, this is a flip-flop, and we have to use this sort of arrow assignment operator. There is also just an equals assignment, and that is different, and the synthesis tool gets mad at us if we use that. So we don't want to use that, and there is a distinction between them, but I'm not going to get into the details of it. But just note that if you're using this always at pos edge always block, just use this assignment operator, this arrows assignment. So we're good. If there are not any questions, we're going to get into it. Oh, yeah, last thing. Things higher up in this are lower priority, and things down below are higher priority. Because what happens is you set something up here, and then if you set the same signal down here, it'll get overwritten. Just, OK. Yeah, I'm going to ignore this for now. So we're going to go over here, and this is the actual code. So what we want to have, what we want is we want a 15-bit register. So it turns out that if we want a register in Verilog, it's the keyword reg. And so we're going to need a 15-bit register, so we're going to need a bus. So this is going to be 14 down to 0. And then the name of the bus, or the name of the register that we want. And this is going to be counter. And there we go. We now have our very own 15-bit register. So now we want an always at pos edge I clock. And this is going to generate us a sequence, a flip-flop. So we're going to do a begin, end. Is everybody following along okay? Okay. So we need to, just to start off, we want to reset this register if we have a reset signal asserted. And to be very specific, this is a synchronous reset because it only happens when we have a rising edge of our clock. So we have if not I reset set n. Begin, end. Okay, so now what do we want to do if we have a reset signal? What action do we want to perform? I'm going to call for audience participation here.
If you have a reset, you want to clear it.
Okay, so yeah, so if we have a reset, we want to clear it. So what are we going to, what should I write here to clear this register?
When you want to set all your bits to 0?
Yes, so yes, that is correct. So what was stated is we want to set reset all the bits to 0. So what we're going to say is we have this variable counter that's storing our state, right? So we're going to say counter, and we're going to use our fancy assignment. And so this is actually where this other slide, this is what this slide was getting at. So if we have, because note, our register is more than 1 bit wide, right? It's 15 bits wide. So we need to use like bus assignment. So we can actually, there's a little bit of a distinction here. But we have we've defined a register, we've given it, our MSB is bit 14, our LSB is bit 0, and we've given it a name. Now, so now what we want to do is we want to assign to it, so we've used the this arrows operator. So there's like more than one way we can do this. So if we want to just be kind of the like low number of characters way is we can just assign this to 0. And so we're going to have a defined width constant. So it's 15 bits wide, and we have our single quote, and we're going to say that this is decimal, so for a D, and then we're going to set it to 0. There. So we could also, if we wanted to, like, reset it to this counter to be a certain value, what we could do is we could say counter, we could just change this value to be some other decimal amount. But we could also just set a single bit in here as well. So we could just say, I actually just want the third bit to be set. So note that this is 0 indexed. So this is the third bit. So index 2 is the third bit. And we're going to just say this is equal to 1B1. So that sets the first bit. The synthesis tool is probably going to get mad at me about this. So what I want to do instead, if I want to just set that random bit in the middle, is I'd say that this is 14 down to 3, comma, 0. So you can sort of slice into the register. And then this isn't a 15-bit constant anymore, right? Or this would be, 1 down to 0. Does this syntax sort of make sense? And I'm sorry that the screen is so small. Can I zoom in? There we go. Can you see that better? Sorry about that. I forgot that the screen was going to be so small. That better? Okay. So we can slice in, and this isn't a 15-bit wide constant anymore, is it? It's a 14-bit wide constant. So that would need to be 14 there. That make sense? So like this is all like sort of syntax stuff. And so like as you write Verilog, this like becomes easier. But just sort of, I just want to expose you to some of this stuff. So we're just going to set this 0, and we're going to set the whole thing. And so if we're setting the whole register, you can just call it by name. So there we go. So now we have our register, and we can reset it. So what do we want to do here? So overall, we want this register to count up. Ideally, we want to count up on the rising edge of the reference clock, but we're going to not do that right now. We're just going to have it count up on the system clock. So doing that, what's the next thing that I should write? Okay. So we're going to just add 1 to the counter, right? So we're going to just increment the counter. If we're not getting reset, we'll increment the counter. And since it's a 15-bit counter, it'll overflow at the correct time, and it'll just wrap back around to 0, and everything will be happy. So we're just going to do counter plus. So you can just use like your plus operator here. And we're going to say it's 1 or 15 D1. And I think, and this should actually work even if I don't specify this as being 15 bits wide as a constant. The tools will kind of like figure it out for you, like what the width the constant should be in order to work correctly. But I always like to just use the correct width in my constants just to make sure everything works out nicely. So what we have here is this should actually build for us a counter. So we're going to test this out. So here next in my slides is we're going to run this script called netlist.svg.bat. And this is actually just going to open up a web page for us. So I'm going to just go to the web page. netlist SVG. So we're going to open this up, and this netlist SVG demo. And so what this does is it lets us make fancy block diagrams like this one shown. And this is how I've generated the block diagrams for this, this presentation. So I have another script. This is called this elaborate JSON.bat script. And what this does is it's actually running the elaboration tool and then outputting how it thinks the block should look to a JSON format, and then copies that code over to the clipboard for you. And we can copy paste it into the web page, and it'll generate us nice looking block diagrams. So if we want to do that, what we're going to do is we're going to go over to our tools that we opened earlier. So you should have this OSS CAD suite document here. And for those online, if you're using Linux, there's a equivalent script called elaborate JSON.sh. You can just run that, and it runs equivalently. So we can do elaborate JSON.bat, and we need to provide the script, so I'll just run this. So this provides a usage. So elaborate, and we're going to provide the name of the top level module. So if we go over to our code again, the module is named ClockGen, so we're going to call it ClockGen. And then the name of the file. So this is source input clockgen.v. So that's going to run. So this actually generates you some code, and I think it's not super happy with what it generated. It probably has some, at least some warnings in there, but I'm going to ignore them for now because I'm pretty sure this works. We're going to see if it works. See if I was proved a fool. I'm going to paste this in, and it's going to render. Oh, no, it did not like that. Yeah, it got mad. So we're going to see. Oh, OK. So this elaboration tool was actually very smart. So note, what do we have here? All we have is a bunch of inputs and outputs. The elaboration tool looked at our design, saw we weren't outputting anything, and said, I don't actually have to do any work. I can just make you an empty module, and that will do everything that you actually did in this module. So it just got rid of my design. So this is kind of an interesting thing to happen there. OK, so to get around that, what we're going to do is we're going to actually, I'm going to introduce one of the things that was supposed to be just a skosh later in the PowerPoint presentation. We're going to go back. You get to see some of my memes there. So OK. So what we have is we're going to need to do an assignment statement here. And this is just generating you combinational logic. So we have this AND gate and this NOT gate here. So what we're doing here is we're just doing an assign. We have a wire name, and then our other signals in our test bench. And if we have this, we can infer. So before, in our always block, we were generating this flip-flop, right? Here, we basically are generating this combinational logic. So that's what you can, and this just lets you assign output wires and et cetera, et cetera. So, OK, yeah, here we go. So we're going to go back to the code. And so what we want is we're going to assign 1 hertz strobe. This isn't actually a strobe signal, I will note. And we're going to do just a normal equals operator here, because Verilog. And then we're going to say, we're going to grab the highest output bit from the counter. So we're going to say counter 14. So that's the top bit from the counter. And with that, we're going to try running that script again. So if we go over to here, I'm just going to up arrow. So we're going to run that script again. Yeah, OK. Note this output here. So look. It actually generated us stuff this time. So it generated us 10 wires, wire bits, et cetera, et cetera. And here, note right there, we're generating 1 flip-flop. And just a side note on how the elaboration tool works, it says that the register is 1 flip-flop. It's actually 15 flip-flops, but just, it's like grouped as one module, so it shows up as one flip-flop in this output list here. So we're going to go back over to here. We're going to copy, paste. Oops. Yeah, we're going to see if that worked. Yeah, so there we go. No, we now have a counter. And so like this is how you can like see that the elaboration tool is actually doing what you want it to do. Because what we wanted was a counter, and that's actually what we got. So see, we have our register. We're going to add 1 every loop to the register, and then if we're resetting, we just assign the register to 0. Very cool. So, and then this is just saying that we're grabbing the top bit. So we have a counter now. So we have our counter. Now let's see what this looks like in the simulator. So what we're going to need to do is we're going to need to write a test bench for this module. So if we're going to use a module, we need to instantiate a module, right? So we take our module name, and so just in general, the syntax looks something like this. We have our module name, we have a parameter list, so you can, Verilog has this thing called parameters, so it lets you, like, if, for example, you wanted to have a counter with a variable width, but you don't, it's like the same code every time, it's just like a generic width. You can like set something like that in this parameter list. I'm not going to use it for this workshop. I'm just going to like note that that's there, that's the syntax for it, etc. And then we give it our module, our instantiation of the module, a name, and then we have our open parentheses, and we have our dot, port name 1, and then open parentheses, the signal that we want to connect it to at like the test bench level. We do that for every port in the module, and then we close paren, semicolon. We're done. And this is just an example of that. That's what that looks like. Okay, so let's do that. So what we're going to do, yeah, I'll get to this later. So is everybody following along okay online, or is there questions?
There's an issue with the JSON script.
Oh.
Side we can handle on the break.
Okay. Let's go through the yeah, we'll go through the test bench, and then we'll like, I think that'll be a good point to sync up. Okay. So so what we want to do is we want to open up the test bench. So I have provided in the, so at the root level, there's this test folder, and this has all the test benches for the project. So we're going to go open up this clockgen.tb.v file. So this is a test bench, and this is like, it's kind of fancy. I've provided you like, I feel like a fairly nice test bench infrastructure, but we're just going to use the basics of it now. So what we're going to do is we have this module that's our test bench. So in Verilog, our test bench module is also a Verilog module. And then what we do is I have all these like top level signals that we're just that just are at the test bench level. And then I have some extra stuff for like doing timeouts and things, and that's nice if you're send this up to the tiny tapeout actions, because sometimes you'll just run a test bench and it'll just kind of loop forever. And you're not getting much info out of that, and so you have to stop it. But I have this timeout so that if it doesn't get periodically reset, it'll just end the simulation prematurely and give you an error. So what we're going to do is we need to instantiate our clock generator, that module that we just wrote. So what I'm going to do is I'm going to grab the module. So we're going to grab the module definition, copy that, and we're going to make an instance of it. Tab, paste. So our module name, or our module type is a clock generator, and we're going to call it our clock gen inst. Just a real generic name. And then I'm going to make the indentation okay, and we're going to give everything dots. So when you are defining ports to your module, everything needs a dot on the beginning. So that's just the syntax. So we're going to hook this up to the reset signal. So this is reset, reset, n. We're We're going to hook up the clock to our Testbench clock. So that's up here. So this is going to be clock. We have our, oh, I'm missing that. Okay, so we need, I forgot, I should have had this in here. But we're going to also need a reg ref clock equals 0. So we're just going to start up. So like I said, this is more like how you do it for an FPGA, but we're just going to define its initial state here. And we're going to say, oops. Copy, paste, half period, and we're just going to say this is 203. Okay. And then we're going to ref clock. So what basically this does is we have an always block that just is going to toggle our system clock and our reference clock just all the time. And that's just what it looks like as a test bench. So we have that. So now we have our ref clock. So we can say ref clock as our input there. And then we need some wires. So this needs to hook up to our test bench. But this is actually going to be, our module here is driving the outputs of the test bench. So we don't want those to be registers. We want our module to drive those. So those are going to be wires, wire, clock, 1 hertz strobe, wire, clock, O, slow, set, strobe, wire, clock. Oh, wait, that shouldn't be an O there. There's 2 there. That's better. Fast, set, strobe. And then wire, debounce, strobe. And now we just copy all of these into our module. So that's going to be clock, 1 hertz, strobe, clock, what did you do? Okay. Clock, slow, set, strobe, clock, fast, set, strobe. And then finally, clock, debounce, strobe. There we go. So now we have that module set up. So we save that. Save that. Okay. So that should be enough to instantiate the module. So now we need to actually run our module. And we're just going to let this run for, I'm just going to say repeat 10,000 clock cycles. And pause edge clock. So this is, since we're not actually interested in synthesizing this Verilog, we can kind of do whatever we want in the test bench. In terms of like how I said, you don't want to do this pause edge stuff on anything other than the system clock. In our test bench, we don't care. Yeah, question online?
Quick question. Would it just be debounce _stb instead of clock _debounce _stb?
Yes, you were correct. Good catch. Yeah, that would have showed up as a error when we were trying to run it. I might actually just leave that, and we'll see what the error looks like, because I do this all the time. So we're just going to let this run for 1,000 clock cycles. So, and then we're going to run this in the simulator, is what's going to happen. So with that, let's go over to, I have this in the README. So what we're going to do is we need to run Icarus Verilog. So this is the simulator for running Verilog locally. That's going to look like, so basically we have to, what's called the elaborations, or we need to like elaborate it, so it needs to, that'll run like all the syntax checks and stuff on our files. And then what we do is we run the simulator. So we're going to start by pasting this in. So we're running iverilog-o, and this is what the output file is going to be. And then we provide it the input files. Okay. Was it getting painful watching me use the? Okay. We're going to use the correct terminal this time. So this has to be the terminal that has the open source CAD suite enabled. So we're going to paste that in.
I don't know when they said it, but they want you to run PWD. They want to know which.
Oh, okay. Yeah. So I am in. So you can actually see it here. The Windows terminal doesn't have PWD, very annoyingly, but it just shows up here. So we're in the root directory of the GitHub repository. So if I do a dir, so you can just see where we're at. So we have source, start.bat, all of this stuff available to us here. Does that make sense? We good? That close enough to PWD? So, okay. So this is the output file. This is the name of our test bench. This is the name of our file. And this is actually going to be mad at us. But we're going to run this. Okay. So, like, as was mentioned online, we have a problem with the name. So hopefully you can see this on the screen. But we have, it gets mad at us. Clock debounce strobe is not defined in this context, so it's mad. So what we want to do is we want to fix that. So as was mentioned, we need to go through save. Alt-tab, over here. Now we just run that again, and it's going to be mad at something else. Oh, it's mad because I don't have the sim directory. So I'm going to make dir sim. I'm going to run that again. Okay. Okay. So, yeah. So now we have that. Now we can run VVP sim clock gen tv.bvp, and we want to add the option -fst. This, by default, Icarus Verilog generates VCD files as output. That works. The problem with them is they're really big. So if you add the -fst option, it generates compressed output dumps, which are much easier to use. So we're going to run that. So this ran the test bench. So like I've hooked up a bunch of stuff here just as a template for you all to use. We can go into that in more detail if people want, but I figured it would be better to just kind of start off, just kind of use it. But yeah, so now we're going to run in this other window that we have open. So I have two windows open that have the OSS tools, open source tools installed. So we're going to now run Gtkwave. And we can actually just run it on the output dump we have. So I am currently in the same folder I'm in over here. So I'm going to run Gtkwave, and I'm going to run clock gentv.fst. That's the file that we generated. And you can change the file that gets generated by your test bench. So if we look in this test bench, the source code, so we have this initial begin, and we have this dump file variable here. So this is the name of the file that Icarus will generate for us to look at. And also note that the dump variables this has to name has to be the same as the module name that we've given our test bench, just as by way of note. So we're going to run Gtkwave. So it takes a moment to start up, but here we have it. We have Gtkwave. Might be a little hard to see, but if we run that, so we see our instance. And this, if we just click on this, we see all of our top level variables. So we have our clock signal, and then this is the output signal that we have from our system. Note that we have undefined here at the start, because when we first start up our module, we haven't given an initial state to our register. So, but what happens is, and we only have a synchronous, go to the beginning. I'm at the end. we only have a synchronous reset. So if we look at our reset end line, note that it doesn't start till the second clock, and also our output isn't asserted until then. So there we go. We have our clock 1 hertz strobe. I'm going to zoom out, and apparently we didn't run it long enough. So I am actually going to change the simulator here so that we see its output a little faster. So we're going to, instead of grabbing the 15th, we're going to just grab the first output.
Someone else got an error for opening Gtkwave online.
Oh, okay. What was the error? Just not found?
It says, no symbols in PCD file, is it malformed?
Oh. Okay, did they add the -fst tag when they were running VVP? So I can actually just run that now. So if I run VVP without that FST tag, so we'll run that, it finishes correctly. But now if we go over to Gtkwave, if I try and refresh that, it's going to be mad. Let's see. If I go over to here, so I think it should be mad. Yeah, it's mad at me. It's kind of erroring out, I think. Yeah, see, it's not happy. Yeah, I can crash Gtkwave real time here.
He said that, so he's good.
Yeah. Yeah. I don't want to report to Microsoft. Okay. Yeah. So yeah. So there we go. The FST flag is important. So we reran that. Now we are going to reopen Gtkwave. We should be able to just hit the refresh button and see your output, but since I crashed it, that didn't work. So if we zoom out a little bit, yeah, see, there we go. So just for reference, I adjusted it. I had been grabbing the final output register. I changed which register I was grabbing. So instead of grabbing counter 14, I'm now grabbing counter 1, and we can see our output here. I think, does everybody see that? So just by way of, I'm going to just change it again. So we're going to grab output counter 2, just so that we can see what the simulation loop looks like. So if I make a change here, Control save, Control S for save, and then I run over, I go to my terminal window. Now I want to recompile and rerun the simulator. So I'm going to run Verilog, and then it's just that command again. I run that, it's compiled. Now I run the simulator again, and that finished. And now I can go back over to Gtkwave and refresh it, and now it shows the update. Does everybody can follow along with that? So this is kind of our development loop. This is what our development loop looks like when we're just generating these test benches. Is we have our test bench, it kind of provides our input that we expect to the system. And then what we can do is we can edit the Verilog source code file, recompile it, rerun the simulator, and then check our output results in Gtkwave. You good? Okay. So now going back to PowerPoint. So, okay, yeah, this is all stuff related to the test bench, and you can look at this when I give you the slides. Yeah, and we're just going to work on the test bench now. We didn't get to use my meme. So, okay. So now we have our clock signal generated. We have our up counter. Now we need to want to know how to generate strobe signals. So we want to generate a 1 on a signal rising edge. So we need to detect a rising edge. And so how we're going to do that is we're going to hold the previous state, compare the current signal state, and output a 1 when both the previous state is 0 and the current state is 1. And this is what the block diagram we expect for the system to look like. So we see we have 1 flip-flop, and that's going to hold what our previous state of the system was. So that signal's going through here, and then that's getting held. And then what we run is we invert the held state, run it through an AND gate, and compare it to the current input signal. And that will generate a 1 clock signal wide pulse on the output here when we see a rising edge of our signal. So that's what we want to do. And then, of course, we reset when I reset n is low. So what we're going to want to do is we're going to want to put this into a new module. Yeah, let's break here. So if we do that, I'm just going to write this at the end of this current module. So I'm currently in this clockgen-.v file. So I'm going to say, we're going to write a new module. So we're going to say module strobe gen. And we're going to say, open that up. And we're going to have input signals. So our input signal is going to be I reset n I clock. And then we're going to have our output signal, our final input signal is I sig, and then our output signal of I sig strobe. And that's our module there. And we're going to end module there. Now we need a register, so it's reg sig hold, and then we're going to need an always block. So we need a flip flop. So always at pause edge I clock begin end. So with that, we need if not I reset n begin end. And then we say sig hold equals 1b0, right? And then normally we're just going to write in the input. So it's sig hold equals I sig. There we go. So with that, now we need to assign our output. Oh, I forgot to do something here. So I need wire I reset n, wire I clock, wire I sig, wire O sig strobe. There we go. Now, with that, we need to assign our output. So assign O sig strobe equals simply that code right there. We're just going to, I'm going to run this through the block diagram generator real quick. So we're going to do elaborate json.bat, and that's called strobe gen. And then we put this in the exact same source file as previously. So that's going to be in source input clockgen.v. And it was not happy because this is neither an input or an output, because I messed that up. Because I just defined these as wires. They should have been inputs and outputs. So this should be input, wire, input, wire, input, wire, and then finally output wire. Oops. Save. Now we run that again. We have our output. Oops. Control A, Control V, render. We have what we want here. So now we need to basically put these into our clock generator module here. So what we want to do now, oops. So we've now we have a way to generate strobe signals. So we need to generate a strobe signal off the reference clock and then use that to trigger our counter. So we're going to need a clock strobe module and this will be ref clock strobe inst. And this like that, and copy that module definition, copy, paste, add dots here, and then I reset n, I clock, and then this will be I ref clock, and then this output is going to be, we need a wire for it. So we're going to say wire ref clock strobe, and this will be I ref strobe. There, save. Okay, we're going to just start with that, and then, or actually, we need to use that strobe signal here. So what we want to do is we only want to count up if we have that ref clock, if we have a ref clock strobe, so only on the rising edge of ref clock. So we're going to do an if, and then ref clock strobe. So what this does is it's checking what the state of this wire it's checking what the state of this wire is before it will up count, before it does anything that's in this block. So what we do here is then, instead of counting every time, okay, sorry about that. Okay, so yeah, paste that in. So we're only counting up when this strobe signal is high, which means that we're only going to count up once every rising edge of the strobe signal. So with that in mind, we're going to go back to our test bench. And what we're going to do is we're going to say that this, we're going to wait, yeah. We're just going to do this again, and we're going to see what our output gets us, actually. Because, yeah, this is going to significantly delay when we see strobe signals happen. So if we go back to our simulator here, so we're going to rerun our elaboration. It's not happy with me. Invalid module instantiation. So what happened there? It's not happy about, I needed a semicolon. Save. See if that's happy now. Clock strobe referenced once. 3 errors. 5244. I have to call things by the correct name. Run that. Okay, we're good now. So now we run VVP again. And it was not happy. It didn't get any output. And why is that? So let's look at our output here. Let's start by looking at what ref clock looks like. Oh, that's too fast. That's running at exactly the same time. It's probably why this isn't working. So what we're going to do is we're going to run this at 2 times clock period. Oh, yeah. We're going to run at 4 times clock period. We're just going to, that's why. Because I messed up the test bench. I will fix the test bench in the GitHub repository probably tomorrow. Okay, so we're going to run this again, now that that's fixed. There we go. So with that running, we should. So now we have a reference clock here. Now, what we should see is Yeah, there we go here. So now what we can actually do is we can look inside of this module. And we can say, look at what reference clock strobe looks like. And we see that we're getting a single strobe every rising edge of our reference clock. So with that, we have basically everything we need to generate all our reference signals. I'm just going to, I think we're out of time though, so yeah, just show the submission process. I'm actually going to run over, so what we're going to do is, what we have to do for this is you have to push changes. So I'm going to we're going to add this, we're going to add this, and this to our output files, and this as well. So we're going to say, basically what you do is you commit your changes, push them to GitHub, and then the GitHub actions will then run. So we're going to say workshop stuff. Commit. Hopefully. Oh. Okay. I am doing this the bad way now. So we have GitHub pages. I am just, because don't have all this stuff set up on GitHub, I'm just going to upload files directly via the web interface. So we're going to just choose my files, and I'm going to update them manually. So I need to add the info.yaml file, add you. I'm going to add the source. Basically, you have to add all the files that we changed. So this is that file. Need to update the test. Oh, not source test, just test. And tiny tapeout TB, add you. Then we need to add, finally, all the files that we messed with for the strobe generator. So that's input and clock gen here. And also, we need to add the Testbench file that we modified as well. So that's in test. Sorry. And this is clock gen TB. So we add all those files. We put in a commit, workshop stuff. Commit changes. So what will happen now is we should see GitHub actions running. So if you go over to the actions page in GitHub, we see that these things are all running. And so it'll actually start by, for people running Linux, there's a make file. And you can actually run the same make file that tiny tapeout will run. Because this is just running Verilog in the back, Icarus Verilog in the back end. And it's mad.
Sam, there's a comment here. You went over a YAML file edit really fast at the very beginning. What was that?
Ah, okay. So what we did here with editing the YAML file, it's more or less set up. But what you need to add is, I have my information set up here currently, so my name and my Discord. For Tiny Tapeout to work, everybody's modules have to have a unique name. So what you need to add is, change here is this name here. So this top module, this has to be unique for your project. So what we did is we changed this top level name from being the example name, to being this thing that I renamed it to. That make sense? That's the main thing you have to change. You can also change like what tile size you want, et cetera, et cetera. That's the main thing we changed there. And then if we go over to the changes we made here, so we just changed this clock to be the same as what we renamed it to, and it's the same for this. I think that's why that's mad. So that's the main thing. Does that answer the question? Yeah, you can see the repo. I think I've tried to, like, some of that basic tiny tapeout stuff. Matt Venn has really good, solid videos on that are really nice in detail. Like if you just go through his HDL examples, that covers that sort of stuff really nicely. You can also go, I have an example project that is passing, and I'll just show that really quickly. This is not happy. Okay, I will look at that in a minute. But if we go over to my GitHub repo here, if we go to repositories, here we go. Not this one, sorry. This one. This one is running. So we'll note that this is all passed. So what's going on here is this, the info.yaml file is, we're listing out the all the source directories that all the source files that we're using in the project that are under the source dir. And this one's just flat as opposed to the other one. So this just has all those files listed here. But the top level module is this. So this defines the tiny tapeout interface. Note that this name here, this tiny tape TTUM digital clock example, matches the name in the info.yaml file. So also note that this has that same pin interface that is defined by tiny tapeout. Does that make sense? Does that sort of answer the question? That's like the main thing that needs to be changed. You just need to make sure that this module name matches the name in the info.yaml file, and that name is unique. So it's encouraged to use your GitHub username in that file name. That cover it? Okay. If we go back, I'm going to just do a little bit of debugging. We should see I want to see is this. I want to see why the GitHub actions failed, because we should have gotten a little farther in the simulation. So what you can do is this runs the GitHub actions in the back end, and it'll run all the tests for you. So no rule to make target, home runner, source input clock gen -v, needed by this name. So we're going to go to the code and make sure that that code is there. So source, input, yeah, it didn't get uploaded. So I need to make sure, it got put into this root directory. Let's go fix that. Add file. You note I don't usually use the web interface. I want to just make sure, I want to see this, I want to see at least that test run. And now, should run, every time you push a change, the GitHub actions will run. And then when they're all green, you're ready to go. So this is just running this again, and you can watch the action run. And this is basically just running the same simulation that we were running, but in the cloud instead of locally. It's a faster iteration loop is the main, because that's the main thing. And once you like get used to like writing the Verilog, that becomes a big productivity win. So that's the main thing. So yeah, this ran sort of. It timed out on me because the test bench on here is a little different. But because it's actually running the old test bench that we didn't update because of reasons. I know this was, I kind of ran out of time here. We didn't pace correctly. So feel free to reach out to me later if you want to run this. And I might try and upload a separate video on our YouTube channel that just goes through this where it all works correctly. Because it isn't all working correctly here in our live demo here. But feel free to reach out to the chapter email. I think you should all have a link to the chapter website. There's a contact form on there. So if you're interested and you are having trouble getting things to work, just send an email to that and I will try and respond as fast as I can and try and debug with you. But since we are actually running a little late, I'm going to say that that's the end here. Just before we go, I'm going to jump to the end screen just for additional help. Tiny Tapeout Discord is really good. And then sponsorship form QR code. So with that, thank you everyone for coming. I know this is stuff didn't work because live demos, but thanks for coming. Thanks for your interest, and have a good night. And I hope this sparked your interest a little bit, got you interested in learning Verilog a little bit, even though it might have been a little frustrating. But yeah, thank you.